Welcome to lecture 19. In this lecture, we will analyze the performance of the operations of the Fibonacci heap. We will first get the bound for the degree of the maximum degree of a node. We will show that the maximum node degree is always bounded by order of log n. After that, we will analyze the amortized cost of extract min. We will show that it is only of order of log n. And after that, we will analyze the running time of decrease key and show that it has amortized constant time. Okay, so let's begin with the maximum node degree. Let us consider a node x which has degree k at this moment. Now, because of it has degree k, so we can see that it will have a bunch of children. Okay, so let's label the children as y1, y2, y3 up to yk. But we have a special ordering. Okay, so we will because all the nodes will become the children of another node only due to this consolidate process, if you still recall. So the nodes y1, y2, y3, yk will be added as the children of x during some consolidate operation. We will list them, or we will arrange them in the order of the time that they are added as the child. So y1 is the node that is the oldest, the earliest node that is added to x as its children. Y2 is the next one, and yk is the newest child. Okay. Now, let us take a look of what has happened to each of these nodes from the point that it is linked to x and what it is happening now. Okay, we want to look at the degree of the y1, the degree of the y2, and the degree of the yk now. So first of all, we see that each node here, no matter what happens, it has degree at least 0. Yeah, because if it is a single node, it has degree 0. If it has some child, as in that case, the degree is at least 0. Is that okay? So y1 and y2 will have degree at least 0. So we know this. Now suppose that there is a y3, and if y3 is there, then we know that at the time when it is first added as a child of node x during the consolidation, y1 and y2 are already the children of x because they are older children. So when y3 is added to x, y1 and y2 at that time must be the children of x. So in that case, the degree of y3 must be equal to the degree of x when it is combined during the consolidation step. And at that time, x has already joining to y1 and y2. So the degree of x at that time is at least 2. So the degree of y3 at the time during consolidation must be at least 2. Is that okay? But this is what has happened a long time ago during the consolidation. But now, situation could be different because in the Fibonacci heap operation, we may have cases where a node could lose a child. So if a node could lose a child, then in that case, the degree will be decreased by 1. So in that case, previously it was greater than or equal to 2, and now the degree of y3 is at least 1. Now notice that it will not be decreasing by 2. The reason is that when a node loses 2 children, then in that case it will be detached from the parent. So if y3 has lost 2 child, then in that case it will not be a child of x anymore. So it's not there because it's still a child of node x. So it means that it has lost only at most 1 child. Okay, so this is the situation. So let's also see what happens to y4. Okay, we can use the same logic. At the time during y4 added to x as its child during a certain consolidation, the node y1, y2, y3 at that time must be present as the children of X. So in that case, the degree of Y during consolidation must be equal to the degree of X during consolidation. This is the rule of consolidation, right? And at that time, the degree of X is at least 3. So in that case, the degree of Y4 is at least 2 now, because it may lose one child during the time from consolidation to now. And in general, the degree of Yj will be greater than or equal to j minus 2. Okay, so we have actually analyzed what is the current degree of each node. And now let us say nk. We use this nk to be the minimum number of nodes in a subtree whose root has degree k. Based on the discussion above, first of all, n0 is equal to 1. n0 is the minimum number of nodes in a subtree whose root has degree 0. So in that case, we can have a single node. n0 is equal to 1. Now n1 is the case where the root node has degree 1. So the root node may be connected to a node that has also a single node. So in that case, n1, the smallest possible case, could be equal to 1 plus n0. So the root node 1 here plus it is joining to an n0 because the child of the root could have degree 0. In that case, it is equal to 2 for the minimum case. And now for n2. n2 is at least 1 for the root node, and it connects to 2 children. We know that the first child, y1, must have degree at least 0, and the second child, y2, it must also have degree at least 0. So in that case, the minimum number of nodes for n2 is equal to 1 plus the minimum possible for a node that has degree 0 as its root n0, and then another child, this is another n0. So 1 plus n0 plus n0 using this one is equal to 3. Now for degree 3, n3. n3 is a root plus y1 plus y2 plus y3. So y1 is at least degree 0, y2 is at least degree 0, and y3 is at least degree 1. So the minimum possible number of nodes for n3 is equal to this number, and it is equal to 5. And similarly, n4, you get it to be 8. So 1, 2, 3, 5, 8. So these are Fibonacci numbers. So by induction, we can actually show that nk is the k plus 1th Fibonacci number fk plus 1. So because of this, that's why the heap that we are studying in these 2 lectures, we call it the Fibonacci heap. Yeah, because there is the hidden Fibonacci number in the analysis. Now actually, the k plus 1th Fibonacci number is at least the golden ratio to the power k. The golden ratio is this number, square root 5 plus 1 over 2, which is roughly 1.618. So in that case, nk has to be greater than or equal to 5 to the power k. So because of this, the degree of any node cannot be a lot, because the maximum degree nk, and if k is the maximum degree, then we have to satisfy that nk, the tree has at least nk nodes, which is 5 to the power k. But on the other hand, you can only have at most n nodes in the tree. So it needs to have n to be greater than or equal to 5 to the power k for any k. So in that case, doing this opposite analysis, we will find out that the degree of any node cannot be more than log of n base golden ratio. And this is roughly 1.4405 times log of n. So this shows that the maximum degree of a node is of big O of log n. Okay, so we have done with the first part. And now let us analyze the cost for the operations. Mainly, we want to analyze the amortized cost for extract min and also the decrease key. But first, let us recall what has done for insert, find min, and union. Okay. When we do the amortized analysis, here we are using the accounting method. So accounting method will invest certain money for each operation. And then when there are excess in the money, then we will store it associated with the nodes inside the tree, inside the heap. Okay. So here we will show the following invariant. We will keep the following invariant. Okay. The excess will always be there. Okay. So that every tree root will have $1 at least for it, and every marked node will have $2 for it. So the excess will be distributed into the nodes, and then for each tree root there will be $1, and for each marked node there will be $2. And we assume that the tree roots are all unmarked. Okay. Now for insert, we will set the amortized cost to be $2, so it is constant. Okay. Now after inserting a node into the tree, we will have one extra node as the tree root. So we will use $1 for the actual cost for this operation to create the node and then to update the minimum pointer if needed. So this is the $1 for this actual cost. And then because the amortized cost is $2, so we will have $1 left. So the $1 left as an excess, and it is stored in the root for this newly inserted node. Okay. Now for find mean and union, we do not create any extra trees. Okay. So in that case, the actual cost is just 1, and then we can set the amortized cost to just $1. That's enough. So in that case, this amortized cost of $1 will be enough to pay for all the actual costs in this find mean or the union operation. So find mean, just report the minimum. Union, just need to update the minimum pointer. Yeah, so all of them, they have the actual cost of order 1. So $1 will be enough. Okay, now let's see extract mean. Okay. Recall that during the consolidation step, we will use an array A such that AK stores a tree whose root degree is K. So we will use this to facilitate the consolidate process. Okay. Now, this is how we are going to use the excess to help pay the operation here. So when we process a tree with root degree K, we will use the excess to pay for the following things. Okay. We will try to add this tree to the array A. So this takes some cost. Is that okay? And then we may link this tree as a child of another node. Yeah, because when we see two trees that has the same root degree, one may be linked to the other. And after the linking process, we will create a larger tree with a different degree. So we will move the combined tree to another entry of A. So this movement also needs to do some cost. Okay, and in that case, the excess of the roots will be paying these two things. We will see that it will be added to the array at most one time. It will be added as the child of another node at most one time, so that this will create a movement of at most one time. If we further need to move this again, then this is not the business of this node, because it is the new root that takes care of the another movement. So all these two cases, they are only constant time. So it is with the excess of $1 stored in the root, it is enough to pay for the adding and also the linking of these two processes. Okay, so what does that mean? So apart from the initialization of this array A, all the actual costs in the consolidation will be settled. So we don't need to pay for the consolidation using anything extra. We just need the original excess is enough. So now, the amortized cost, we see that we only need to handle the following. So first of all, we need to remove the node with the minimum value. And this will create at most order of log n new trees. Yeah, because after we remove a node, it will cut all the linking between the node with its children. And we have already proven that each node has degree at most order of log n. So it takes order log n time to remove a node. And also, we will need to initialize the array A. So array A has order log n entries, so the initialization also takes order log n time. And after that, we have the consolidation. We don't need to pay. But in the end, since the excess of all the root nodes are already used up during this consolidation, in order to resume the excess that we need to store in the tree roots after the operation, we will recharge the excess of the final tree roots. But we know that finally, the tree roots will all have distinct degree. Yeah, because these are the trees that is left within this array A. So there are only order log entries remaining. So if we recharge the excess $1 for each root, then the total cost is order of log n. So log n, log n, log n together is log n in total. So that means that for the extract min operation, order log n amortized cost will be enough. So we are done. Okay. And finally, decrease key. Okay. So to perform decrease key of a node, we will set the amortized cost to be $4. Okay, so $4 here is again it is of order of 1. So we will analyze what happens for decrease key. Okay, so there's different scenarios. So first of all, when we do decrease key, okay, the best scenario is, the best means that we don't need to do a lot of things, is when the current node is not detached. We just decrease the value and then we find that the heap property is still okay. So the actual cost is just 1. And then the amortized cost is $4. It is always having enough to pay. So we're done for this case. So $4 will be enough for this scenario. Now when the current node is detached, then we can have a good case as well when the parent is unmarked. So it could happen when the current node is detached and the parent of the corresponding detached node is unmarked. Then what do we need to do? Okay, the actual cost is just constant and there is no cascading cut, so constant for actual cost. And then we use $1 to put into the current detached node. This is stored as the excess in the current detached node because it now becomes a root. Root node has $1 as its excess. And also, the parent node will now be marked because it has lost the first child. So when the parent node is marked, then we will put up this $2 as the excess stored in the parent. So altogether, 1 for the actual, 3 for the total excess, so $4 will be enough. So this is the case when the current node is detached but the parent is unmarked. Okay, what is more complicated is the following. Okay, so there will be an event of cascading cuts. Okay, so when the current node is detached and the parent is at this moment, before the detach, it is already marked. Then there will be cascading cuts. Okay, the current cut is not cascading. The cascading cut is when the marked node is detached from the parent. Okay, so we let C to be the number of marked nodes in these cascading cuts. So for each marked node, then since recall that each marked node we will have $2 in our setting. So for each marked node, we use $1 of the excess stored in the marked node to pay for the related actual cost because it is now detached from the from its parent. So the detach of it from its parent. So it costs 1. And also because it is now becoming a new root. Okay, the root of a new tree. So $1 is left. And then it is kept as the excess inside the node because it is now a root. And it is now unmarked as well. So in that case, after this operation, all the cascading cuts are paid by the excess. So all actual costs related to cascading cuts are settled. And what is not settled is the current node is detached. So what is not settled is we need to pay $1 to handle the current node for this cut. And now this current node after detachment, it becomes a root. So we will store $1 as the excess. And again, for the final cascading cut, we will make a node which is the parent of the last cascading cut node. We will change it from from unmarked to marked. So in that case, we will put $2 inside it as the excess. So altogether, our amortized cost needs to handle this one, $1, $1, and $2. So $4 for the amortized cost will be enough. So this is a summary of the performance of the operations. So when we do not have this red rectangle, all represents the worst case cost. The red rectangle represents the amortized cost. So we will see that for binary heap, the union is bad. It is of order of n. But for binomial, mostly it is very good. All of them is of order of log n. And for find mean and make heap, then it can be done in constant time. And for Fibonacci heap, then we will see that all the costs in this one or the union, they are worst case actually. So order 1, order 1, order 1, and order 1. And for extract mean, decrease key, and delete, we have proven this is the amortized cost. So for extract mean, order log n. For decrease key, order 1. And for delete means that we change the value of a node to minus infinity. So we perform a decrease key, and then we extract mean. So in that case, it can be done in amortized order of log n. Okay, so that's all for the analysis of the Fibonacci heap. Thank you.